Okay, good morning, everybody. Let us start. Let us discuss the case of pure strain. What is pure strain exactly? Generally, the term pure strain is means that there exists no compressive, but only tensile strains are there. And when the cylinder, there may be other explanation also. When the cylinder is fairly large, fairly long, the sections that are far from the ends can be considered to be a state of plane strain. Means if the cylinder is like a pipe or the cylinder is the pipe itself, the section that from both the ends can be considered to be a state of plane strain. And we assume that sigma z does not vary. Means in the log sigma z is the we are using r theta z as our coordinate axis in this case of axiomatic stresses, where r is the distance of the point of our consideration from the origin 0. Theta is the angle that OR makes with the x-axis and is in anticlockwise direction, and Z is the mutually perpendicular axis both to R as well as to theta or both to X or Y. Actually, in case of cylindrical or polar coordinate system, we are using x, y, z, and as well as O as the origin and x, y, z as the coordinates itself. But other than these two, we are having the coordinates of r, that is the distance from our concerned point from the origin, and the angle theta, which makes the line OR with the x-axis itself. So we are not totally avoiding Cartesian coordinates here. Now, if the cylinder is too long and there is no such ends, you see the cylinder is not closed in both the ends, generally stress along the x-axis, z-axis, or stress in the longitudinal direction does not vary at all and does not exist even in some cases. So what we do in the case of phase question is, as this case of plane stress, the question is delta d by dr, the rate of change of r sigma r with respect to r. The function r means the radius and multiplied by the radial stress sigma r. The rate of this change minus the constant sigma theta means the circumferential stress is supposed to be equal to 0. There is no other component anywhere like this. Now, what happened here? In the Hooke's law, we know we have deduced in the ordinary strength of material that ER is equal to 1 by E, and just 1 second. From Hooke's law, epsilon r is equal to 1 by E sigma r minus gamma into sigma theta plus sigma z. Means epsilon r is the strain in radial direction or rate of change of the length of the constant cylinder with the original radius along the radius axis. It is given by 1 by E. E is the Young's modulus, sigma r, the stress along the radial direction, minus gamma, which is the Poisson's ratio, sigma theta plus sigma z. Means sigma theta is in the circumference normal to the radius r, sigma z is along the longitudinal length normal to the radius r. So it is creating, the lateral strain, which will be obtained by multiplying by the Poisson's ratio and adding it to the cylinder constant. As both are acting in opposite direction, so it is subtracting from the original stress, radial stress sigma r. Same is equal to sigma theta 1 by E sigma theta minus gamma sigma r and sigma z, where in this case sigma theta is the circumferential stress and sigma r is radius stress, sigma z is the longitudinal stress, which is acting at normal to the circumferential stress, and so it is creating Poisson's ratio, and thus the eccentricity created by the action of sigma theta itself is being reduced by this term gamma sigma r plus sigma z. Same is equal to sigma z, epsilon z. It is the strain in z direction is equal to 1 by E sigma z minus gamma into sigma r plus theta, where gamma r radial stress and sigma, gamma theta circumferential stress acting normal to the line of action of sigma z. So it is creating Poisson's ratio and reducing the effect of the strain or strain created by the effect of sigma z. So we have got three eccentric, strains along radius, circumference, and longitudinal direction. Now we know there is no stress in the longitudinal direction. There is no strain almost because the pipe is too long or cylinder constant is too long. Its strain is considered to be negligible. So it is f sub z is equal to r. So one you can has the from the equation f sub z is equal to sigma f sub z is equal to 0. So sigma z is equal to r or not r but Poisson's ratio of gamma into sigma area plus sigma area plus sigma r plus sigma theta. So we have these equations sigma epsilon r and epsilon theta by 1 plus gamma 1 minus gamma sigma r and v sigma theta and 1 minus gamma sigma theta minus v sigma minus mu sigma r itself. So 1 plus v divided by E. So we are having the strains in radial direction and in having the strain in the circumferential direction, which is given by the stress along the circumferential direction and the radial stress along the radius multiplied by the different aspect of the Poisson's ratio and Young's modulus itself. Now, if we again solve for sigma and theta from these two equations, we have two unknowns and two equations, so we can solve, but solving is a bit complicated, but we can be done. So E is equal to 1 minus 2 into mu plus 1 plus mu into multiplied by V into epsilon r plus 1 minus multiplied V into epsilon plus 1 minus gamma into 1 minus mu into epsilon theta itself. Just 1 second, please. That is sigma theta. So sigma theta, what you are saying that it becomes sigma r and sigma theta similarity. Both are multiplied by E divided by 1 minus V into gamma plus 1 plus gamma and divided by 1 minus V into gamma 1 plus gamma. Here inside the bracket for sigma theta gamma into epsilon, here 1 minus gamma into epsilon and 1 minus gamma into epsilon theta gamma epsilon theta itself. So what we are having now, we can substitute for sigma epsilon theta and epsilon theta from equation 3. The above equation will come. What is what we have in what we have in equation 3 and 4? That is on equation 3 and 4. And in equation 3 and equation 4, what is given is f sub theta is given as u1, the displacement along the radius direction divided by the radius itself, divided by r, which is the radius itself. So you can put the value of ur by r here, and epsilon r is represented by dur by dr. So we can put epsilon dur by r here, and here we can put ur by r. So dur by r, and here dur by dr, then u by r and q by r. So we have got substitute this equation of equilibrium 5c. We know the equation of equilibrium 5c is given as d by dr r into sigma r minus sigma theta. So we have got sigma theta here like this, sigma in this form, and if you put this form, d by dr r sigma theta, which is given as minus d theta, and minus d theta, we can put minus d theta here, and r sigma r is given here. So dr by r sigma r, and which is multiplied by r minus v ur minus this is equal to total this sigma theta itself, and we could put it here. This time is common to both sides. This e divided by 1 minus 2 gamma into 1 plus gamma is common to both sides, so it has become so that this equation will become this position, as well as this portion of the equation staying from here multiplied by d by dr, or this portion of the equilibrium stays there multiplied by it stays there and add it, because r dr, this is the portion here, this 1 minus 1 dr by the into r here in terms of d by dr, and epsilon theta is this portion, r into dr by dr, 1 plus gamma into ur by r. So what we are having here, if we make the derivation accordingly and subtract these equal terms, like say, it will become dur by dr divided by this into gamma into ur. So if you divide, this will be dur by dr, and r dur by dr itself minus, here we will get another, if we multiply it here, if we break it, r square into 2, r plus r dr, and so we can make derivative and get this type of equation here, where this equation will cancel each other. Here ur by r will stay only here as minus, and plus r mu r by c will cancel from here. So after simplification, we are getting dur by r plus r d square ur by d square minus ur by r. So what we are getting, d by dr dur this portion plus ur by r is equal to 0 itself. Now, it is same as equation 7. For the Plane space, the solution is same as Plane space, because here in order to get ur, we have to integrate them twice, because we have two sets of differential equation. Thus, what we are supposed to do is we have to integrate twice and get the value ur is equal to c1 plus c1 into r plus c2 into r, where c1 and c2 are the constant of integration itself. Now, so from what we have from equation 20 and 21 means that goes up to so what we have from these two equations, this is 20, this is 21, which gives us the relation between sigma theta and ur, and sigma r and ur in terms of other terms. So equation 20 will become C1 that's right. Equation 20 here, if we are putting, if we put dur, just 1 second, please. Then from 20 and equation from the equation here and the equation here, but if we put E1, if you put E1 in respective places, what will have? This will take a form as we will take. If you put dr here, like from the equation itself, it put E1 and dr here, the equation will take the form C1 into C1 minus 1 minus 2 gamma into C square by C2 dr by C2 by R square, এবং C1 minus 1 minus 2 gamma C2 by R square, C2 by R square itself. And gamma square is not R but gamma. So what happens here? E dr by 1 plus R plus dr and once again we can see that here if we add this sigma theta and sigma among themselves, the equation will take the form 2 gamma E, 2 gamma into E divided by 1 plus 2 gamma plus 1 plus V itself into C1. Now, if we apply the boundary condition, at sigma R is equal to minus PA, and when R is equal to A, R means the inner radius, and sigma R is equal to minus PA, the compressive stress inside the inner radius along inside the inner radius, which is equal to sigma R itself at innermost part of the radius itself, and sigma theta is equal to sigma R is equal to minus PB, so R is equal to B itself. So what happens? So what happens here? E and either 1 minus 2 gamma, 1 plus gamma is same, remains same as it is. Nothing, no changes there. But here we are replacing R in case of A square in R squared by A square. Here we are replacing R squared by B square. And we are changing the theta and sigma R and sigma theta by pressure PP here, and PP means inner pressure, pressure at the outermost cylinder, and P is the pressure at the innermost part of the cylinder itself. At the inner radius, this is at the outer radius. This is compressive in nature. This is also compressive in nature. That's why it's magnetic. So the equation reduced to take this particular form. And if you again solve it, then C1 will have this type of equation 1 minus gamma plus this, and E PV being the B square minus PI to A square, A square minus B square. Again, C2 is 1 by gamma PV minus PA, A square plus B square to A square minus B square. So substituting this, if we substitute this value of C1 and C2 in the equation, then sigma R will become PA R square and PA R square A square minus PV B square, Y square minus A square minus PV B square. Sigma theta will become. So we are replacing sigma C1 and C2 will take this particular form, R and theta, and sigma Z. If we add them together, it remains this portion of this thing multiplied by 2 will become 2 into R into gamma into PB square minus A square by 2 like this. It is observed that at the value of sigma R and sigma theta is identical to those of the plane stress case. But in plane stress, sigma theta is equal to 0, whereas plane strain case, sigma Z has a constant value given in 25 case. 25. So what is this? Plane strain becomes 0, and plane stress sigma Z has a constant value given by something. So there is certain strain is going on along this longitudinal direction, but there may not be any stress, but a portion of a sigma Z is created, but without any sort of strain. This is because of the effect of the forces in the radial direction, both inside the cylinder as well as outside the cylinder, creating a lateral deflection along the longitudinal side itself. That's why you are having a value of sigma z in z direction itself. Now, let us go to the stresses in composite bar. Next portion of our lecture, our discussion will be the stresses in the composite screw or shrink fits. What we have here? Here you involve two cylinders made of two different materials, or sometimes maybe of same material, but we get one inside the other. So one cylinder is hollow and one is solid. It may so happen both cylinders are solid or both cylinders are also hollow. So before assembly, the inner diameter, inner cylinder has an internal radius and inner cylinder internal radius A and an external radius C. Here we are thinking that the inner cylinder also hollow as well as outer cylinder. So first we are assuming what is inner cylinder. It has an internal radius A and an external radius C. But the internal radius of outer cylinder is exactly less than this C. They are not equal to C, otherwise there should not be any shrink fit. It is not equal to or more than C, then with that should not be any shrink fit. It is less than C by an amount delta. Delta is extremely small, but it exists. It is not zero. Now, that is the external radius. So internal radius is supposed to be C minus delta itself. Its external radius will be is B. Means outer cylinder has internal radius C minus delta, and outer cylinder, external cylinder is external radius is equal to B. So we are having C at the external internal radius of the inner cylinder. We have A at the internal radius at the inner cylinder, external radius equal to C, and outer cylinder has an external radius equal to B itself, and but internal radius is not equal to C but equal to C minus delta. Delta is a very small, it's a very small amount, but it exists. It is not zero. So if the inner cylinder is cooled and outer cylinder is heated, what happens? Inner cylinder contracts to a certain extent and outer cylinder expands to a certain extent. Then two cylinders can be assembled and one fitting inside the other itself. When cylinder is again brought to room temperature, a shrink fit is obtained. So what we have to do? We are cooling the inner cylinder and we are heating the external cylinder. So inner cylinder is reduced to a certain extent in diameter and external cylinder is increased to a certain extent in diameter. In the same position, if we press the inner cylinder inside the outer cylinder, so what happens? And slowly allow them to go to the room temperature, what happens? They will grip each other and a shrink fit is achieved. The problem lies in determining the contact pressure PC between the two cylinders. And contact pressure PC between the two cylinders. Just 1 second, please. Now, it involves two cylinders. I have just to discuss that. Now, the problem now lies in determining the contact pressure PC between the two cylinders. As their outer cylinder is pressing the inner cylinder is also pressing out externally to outer cylinder for the fitting. They must have a contact pressure PC between the two cylinders, which we are supposed to determine. The above construction is often obtained with three-cylinder, 3-walled vessels to withstand high pressure. In thick-walled, obtain thick-walled vessel to withstand high pressure. For example, if we had a vessel to withstand a pressure of say 15,000 atoms, the yield point at material must be at most 3 lakhs kgf per centimeter square, or 29,40,000 kilopascals. Since such an extremely high strength material doesn't exist in the earth, the string-fitting composite string-fitted composite tubes are designed. So what you say? If we want to increase the size, increase the vessel size of parts is supposed to withstand the pressure of such high, then we have the material which should have such amount of ultimate strength, which will not fail. But no way you can get such material, this doesn't exist. This type of material doesn't exist, so no such high strength material exists. So string-fitted composite tubes are designed to withstand, to make it strong enough to do that, to withstand that material. As if we are using the strength of not a single jackets outside here, but also we are just using the strength of the inner cylinder also. So as a whole, we can face this huge amount of strength itself. This is the conception. The contact pressure itself, when acting on the inner surface of the inner cylinder, reduces the outer cylinder by U1. Now the contact pressure. That is the pressure between the contact surfaces, which acting on the outer surface of the inner cylinder reduces it is outer cylinder to a certain amount UI for inner. On the other hand, the same contact pressure increases the inner radius of the outer cell by U2. So we are getting two more deflection, U1 and U2 itself. Sum of these two quantities, say minus U1 plus U2, because it is reduced, and deflection of the inner outer radius of the inner cylinder is reduced, so it is minus, and deflection of the outer cylinder is increased, so it is plus. So if we add these two quantities, we will have U1 minus U1 plus U2, and this must be equal to the difference in the inner radius of inner and outer cylinder, difference in the radius of the outer radius of the inner cylinder and inner radius of the outer cylinder, which is equal to delta. The difference in the radius of the cylinders, that is the difference in the radius of the cylinder. So we have to now find out, in order to know delta, we have to find out U1 and U2. So we can make use of equation 10. Assume that, what was equation 10? For inner tube, you see, we have here 1 plus gamma, as if we are saying only 1 plus gamma 1 by U1, as if both Poisson's ratio and Young's modulus are different, as we are having string fitted with two different cylinders or by two different materials. So here U1 is equal to V1 by E1, and minus PC is the load acting the outer surface of the inner radius, but it is compressive nature, so it is negative, and others are given same. The outer radius divided by square of the outer radius divided by square of the outer radius minus square of the inner radius, again multiplied by the C itself, C of the outer radius itself, plus 1 plus gamma so C and 1 plus gamma bar mu1 divided by E1 is equal to A squared C squared by C, where again A is the inner radius and C is the outer radius of the inner tube, and divided by C minus PC, the compressive force minus is given, compressive force divided by the outer radius minus inner radius. This is the displacement of the inner radius itself. Or if you reduce further, that is E1 is equal to C1 becomes equal to minus CPC. C is the inner radius, PC is the pressure of the outside surface, C1 Young's modulus, again inner radius, and again outer radius of the inner cylinder. This is the outer radius of the inner cylinder, and inner radius A, 1 minus Poisson's ratio into outer radius, 1 plus Poisson's ratio into outer radius square. For the outer tube, we have in the same process, but we have to replace U1 and E2 are different, gamma 1, mu and V1 are different. V1, V2 are different. We are saying that they are of 2 meter materials, otherwise same. And PC is here, it's creating a tensile force here, so it is positive. Other dimensions remain same as the outer radius is here, out equal to B means outer surface of the outer cylinder, radius of the outer surface of the outer cylinder minus C square, and C plus 1 plus gamma mu2 and epsilon 2. Sorry, C square, B square. C is the inner radius and outside. B is their outer radius and divided by C itself, PC minus B square minus C square. So you have fact U1, have kept U2, U2 can be replaced, be simplified to take this form here. And see, we have gamma 1 minus gamma 2 into C1 and 1 plus gamma 2 into C1, C2. It says C2. And 1 minus V1 that 20 into 1 if this there. The regulated delta is very small as compared to in calculating the U2, which distance of the inner radius of the outer, you have neglected delta since very small as compared to C. Luckily then U1 is supposed to be negative and U2 is supposed to be positive. U1 is reducing in diameter and U2 is increasing in diameter itself. What you are discussing 1 minus gamma 2 by U1, U2 ठीक है, and we are getting PC and PC here as a common item, PC into C into E2. You brought it here, C into PC into E2, and B square minus C square is common here, it is brought here. And here again 1 plus gamma 2 into C square, ठीक है, plus 1 plus V2 into B square. Same is the case like this. So C1, that is 1 plus gamma 2, not C1. Here is also 1 plus gamma 2. I am confusing myself. So here what we are doing, in calculation, you know, we neglected this delta. C is very small compared to C. So now U1 minus U1 plus U2 is the delta. So delta will be equal to, you put minus U1 here. So this minus will get plus, and plus U2. This minus will become minus, and this is equal to delta itself. So regrouping again, the contact pressure P0 or PC is given by delta divided by C1 plus C1 plus C2, C1 minus C2 into V1, E2, 1 we have this plus C square, this square, C square, V2. Thus, this cylinder 2 are made of the same material, then E2 is equal to E1 and V2 is equal to V1. The equation will then be reduced to PC E into delta divided by 2 C square itself. And C square minus BC means these two are same, and so it is kept same. And mu2 are same, mu1, mu2 are same. So the equation will reduce to B square minus C square and c square minus b square minus b square c square. This is important. Note that equation 26 and 27, delta is the difference in the radius between the outer inner cylinder. Now, what we are discussing here, that equation 26 and 27 is the delta is the difference in radii because the inner cylinder and the outer jacket because of sink fluid. So the inner, so therefore the inner cylinder is under external pressure PC. The stress distribution of the assembled cylinder is given here. Here what we are having, PC is this is the stress maximum in the outer here and minimum we are in here, distributed both sides here and both sides here, maximum at the junction, but it is reduced to a certain extent to the circumference itself. If the composite cylinder made up of the same material, it is not subjected to an internal pressure P, then the two parts will act as a single unit and the additional stresses induced in the composite cylinder can be determined from 13 and 14 itself, which equation number 13 and equation number 14 itself. That is the equation given by sigma r, the cylinder subject to internal pressure sigma r is equal to P into A square divided by V square minus A square into 1 minus B square by R square. R is the radius itself and sigma theta circumferential stresses P into A square. A is the outside cylinder, outside radius, and B square minus A square, where B is the inside the radius, multiplied by 1 per B square by R square itself. So the sigma theta and sigma R, we can get this equation at this inner surface of the at the inner surface of the inner cylinder, the internal pressure P causes a tensile tangential stress but the contact pressure PC comes at the same points a composite cylinder stress sigma 13. Hence, a composite cylinder, the internal pressure causes tensile tangential stresses sigma theta, but the contact pressure PC causes at the same point a composite cylinder opposite tangential stresses. This hence this composite cylinder can support greater internal pressure than an ordinary one. However, at the inner parts of the jacket or the outer cylinder, the internal pressure P and the contact pressure PC both will induce tensile tangential stress sigma theta. For design purpose, one can choose the sink fit alloy sigma such that the strength of the two cylinders are equal. To determine the value of delta, one can proceed